All right. Welcome, everyone. I'm Luca. As Bojan mentioned, I both work here at BUAS, but also at Traverse Research, which is also here in Breda. It's about, 200 meters from each other. I want to start with a small comment. My cat ate my presentation. I'm not joking. I've lost some changes, mostly graphical, so there are some slides that don't have the screenshots that I planned and maybe are a bit messier than I thought. Something with SharePoint, you thought that after all these years working as a lecturer doing this exact thing, you will get it right. But somehow I messed it up. I even moved it, I even had it both here and on SharePoint. Somehow the one I moved this morning was messed up. Anyway, the content is there, so just the presentation maybe not as good as I hoped it was going to look. But anyway, today we're going to talk a little bit about some of the things that we stumbled upon and some of the interesting takes from implementing first an inference engine, a compute-driven inference engine in our Rust framework, and then moving it to actually a full-fledged neural network inference and training framework. Because effectively what we wanted to be able to do was not only do inference during a frame, but also train a model, right? So again, I've been working now, most of the things I'm showing here, actually everything is coming from my work at Traverse. And yeah, we've been doing a lot of interesting stuff, a lot of client work, and a lot of stuff related to optimization and making things fast, implementing new techniques. And we figured out at a certain point that we also wanted to make a product, which we called Evolve, which is a benchmark suit. You can try it out there in both of the HP machines that are, they are in this building, but also the other one. These are some screenshots from it, but you can play there. It's gonna come out on Steam and other stores at the end of November, so you could try and grab it for yourself. But yeah, it is a benchmark specifically targeted towards ray tracing and path tracing. You'll be able to run both. But yeah, so let's get to the actual content, right? We're gonna start with a little bit of context about why we're even talking about this. And then we're going to look at two specific use cases that are very involved with the frame. They're not just the traditional, things that we have in production now. So yeah, some history, I guess, on neural networks and machine learning. Disclaimer, this was not generated with AI. I mean, this the presentation, although I did it some other times, but it doesn't really work that well, turns out. Because there has been a lot of hype in the last few years. Right? Maybe a bit too much investment as well. But what we're left with is a surface area on our devices that is specifically dedicated for accelerating it. Is it useful? Maybe, but turns out that when we run our game, that part of the chip might sit idle, right? So we want to kind of use it. And that's where That's the point from which I wanted to take when I started work on this kind of stuff. But turns out that in production, actually, we mostly see very specific approaches, specifically denoisers, super samplers, frame interpolation techniques, and we have seen a lot of both machine learning and traditional techniques. Actually, I think tomorrow we are going to have two presentations about super resolution and frame interpolation and upscaling. But if you look at what is currently out there with like DLSS and OIDN from Intel, most of the techniques in production for machine learning in graphics tend to be about this. And it is a specific kind of approach because they tend to all run convolutional nets, so convolutional networks, on the entire frame. So what it means that, what I mean and why I am pointing out this thing is that it is specifically kind of running as a post-processing operation, right? So we usually take some form of G buffer and noisy output, sometimes reproject it, pass it to the model, and then we present. But this effectively can actually run asynchronously, right? Because potentially when we have the frame ready from our render and our G buffers ready, we can then just feed it to the network, feed it to the model. This could be even completely, it can be run in async compute, but it can completely be moved to the AI accelerator or even an MPU if you're on mobile. So there are a lot of options there. And that is not particularly interesting, and that's why we're not going to talk about these techniques today. But that's indeed what we currently see in the industry being used. And again, there are a lot of techniques out there already for this. What instead we're going to talk about today are techniques that are a bit more involved, if you may, right? So that the network output is actually used in the current frame. The current frame is dependent on their output. And for example, one of them is NERF. I'm pretty sure all of you are familiar with it. We're actually not going to talk about it. But then we also have seen recently advances in neural radiance caching, as you probably have seen as well. And finally, also neural materials. It's actually the other way around. I'm going to go through it. But all these three techniques we have tried to experiment with in our engine. We have implemented a version of it with some successes, with some failures, but we have learned a lot on the way to where we are now. And yeah, today we'll mostly focus on the last two. And the other interesting part is that all these three models share a similar architecture. They have an MLP, or a multi-layer perceptron, which is probably the most common neural network that you can find out there, right? I'm also today not going to really try to explain to you much about neural networks themselves. There are better videos and stuff out there that you can access. But we are going to focus on some specific implementation details and decisions that we had to make when implementing them and trying to optimize them for those specific use cases. The other difference compared to the previous techniques that apply convolution is that they actually are evaluated per intersection. Some of them, like NERF, is actually intersection on the volume. Instead, neural radiance caching and neural materials are intersection on surfaces, right? So we need to evaluate the intersection before we can continue tracing or we can present the output. So that presents obviously a big challenge. So how did we get here? We started neural network-based technique, trying to implement and research neural network-based techniques back in 2021 when I joined at Traverse. But at the time, we were specifically only interested in implementing our own research in neural materials. That was the first step. So yeah, we mostly focused just on getting inference going. And also at the time, of course, less options were available than now. Although there were some interesting development already happening in DirectX 12 and on Vulkan, where we were seeing with matrix intrinsics and cooperative matrix intrinsics, although most of them were only available on NVIDIA at the time. The support is improving, but at the time, that was the only option, but at the same time, it gave us a good idea that maybe it would make sense for us to implement all these techniques in compute shaders, and then we could eventually actually use our hardware acceleration through these intrinsics, right? That was our idea back then. And now you probably also stumbled on some new interesting development like Slang and Slang-D. But also we evaluated that, and at the time didn't really make sense to invest in that. Although there was a lot of development, and now it's also part of Kronos, if I'm right. So the development of that is also going to be quite interesting. But yeah, so we wanted to start with something that we could integrate in our infrastructure. Thus, we actually built it on top of our render graph. And I think this is the kind of the TLDR of the talk in a way. We had a pretty decent implementation. I mean, actually a good one. I managed to implement everything that I needed quite smoothly of a render graph. And this also follows a bit the architecture they usually use for inferencing and training network, because at the end of the day, they tend to just be computational graphs that you traverse forward and then backward to propagate the gradients. So at the end of the day, you're still going to build a direct acyclic graph, and you can do all this kind of operations. So obviously, it made a lot of sense to build on top of this. On top of that, we also have bindless. We also have allocation, cross-platform allocation. So we wanted to build everything around that. So basically, our tensors would be just other buffers or other textures, and they could communicate seamlessly with the actual with the render loop, right? So the first, this is the first, I think, good-looking version of the neural material that we implemented back then. Again, unfortunately, my cats ate the presentation. I had more recent ones on the next slides, but that's what we're gonna look at for now, at least, unless magically it recovers. But effectively, this technique, it's based on bidirectional texture functions, a pretty old technique to represent materials, by starting from captures from different view and light directions, and simply interpolating through them with various techniques. One of the most common one was probably doing clustering, and then using the clustering to interpolate based on the current UV, WO, incoming and outgoing direction, right? The cool thing about it, I think at least, is that this approach allows you to both take real-life captures. This example that you saw here, where, for example, were trained on data from the dataset from the University of Bonn called UBO 14. While instead, of course, you can also synthetically generate using bespoke rendering, right? So as long as you can provide captures of a material, then we can use this to represent, which basically allow you to have a unified pipeline that you can take something from the real world, you can take something that your artist made, and you're gonna get what you see. So whatever you export, you render with your renderer, color-wise, you're gonna get exactly that back. So it could be an interesting, it could be compelling from artists from that point of view. But of course, this system has each model overfit to a different material, to a specific material. So effectively, in these images, all of the materials apply to both those cloths and also the floor, where neural materials train in this way. But all of them are actually completely different models, right? The architecture is the same, but the model is different. So there is absolutely no generalization of any sort. But that's not really a problem. Performance-wise, they restarted. So effectively, what these techniques do is replacing the BRDF evaluation with the neural network evaluation. And that's very costly, of course, right? And on top of that, they don't actually do properly sampling. And we treat them all as diffuse, effectively. We just apply a cosine-weighted sample over the hemisphere, and we just continue this. But as you've seen from the pictures I had before and the picture I was supposed to have here, you actually still do get specular highlights. Because if that is in the data that you exported, you're going to find it back. You're just not going to find exactly the reflections as you would expect, but the specular highlights and all the kind of effects like subsurface scattering, if you have it and whatnot, you're gonna find them there. But yeah, again, there were some recent techniques that also introduced sampling and PDF estimate. Maybe that's an interesting direction for the future, but at the moment, that's what you were looking at. But again, this means that we need to run inference for each pixel, intersection, and light, even worse, right? For every direct light evaluation, we need to sample the network. So not just for a view direction, but also for the incoming direction. So again, not completely ideal, but still doable. There are mainly two components in this system, or better, two models. There is an offset model and a reflectance model. The offset model effectively uses just traditional parallax mapping. The model outputs a scalar that is the offset that then we input in traditional parallax mapping. So the geometry information is kind of preserved like that, right? And then we have the reflectance model, which, well, as the name says, gives you back the reflectance that you can multiply by the light that is incoming. Both models are made up of two learned components, what I usually like to call neural latent texture pyramid or 2D grid. Effectively, every taxo in this, or every voxel, if it's 3D, in a latent grid, it's learned. And then potentially interpolated. In this case, it's interpolated bilinearly, but everything is learned. And we assign just something like 4 floats per level, and those are just going to be fit. It's kind of like taking a step back from the representation, the PBR representation with all the maps that we use there, and instead being just like, okay, there is an empty canvas, try to fill it in the way that makes most sense, right? Obviously, that doesn't work like that. We don't talk with AI. Well, you do if you go on chat with chatbots, but this is not one of them. And then we also, of course, integrate it better with our renderer, use it with our GI, and also have parts that were unlit. We also export an albedo/base color texture, which effectively is just computed offline by averaging, of course, using cosine weighted, averaging the RGB or the reflectance network inference. And it's evaluated for each taxo and by sampling n direction. We found that, of course, we found that about like 32 directions for both incoming and outgoing directions were enough to get an average that looks like it makes sense. And you saw it maybe in the previous slide, when it was unlit, you could still see everything. Another interesting part is that because of that, any time that you hit with the primary intersection, the material, you always do the offset. You always run through the offset network. Then you use this offset, you can use this offset either to sample the albedo texture, so you also have these effects from parallax mapping that are quite accentuated by this network, or instead you actually use it to then query the latent texture that is stored in the reflectance model. So again, both of them have both a latent texture and then an MLP that is connected right away to it. The offset model, the only difference is that it takes the incoming direction only, the view direction only as input, while instead the reflectance model takes both the view direction and the light direction that are currently evaluated. Again, an interesting thing about the learned texture pyramid, then that's the reason why similar techniques have been used so much recently, or at least using grids, either hashed or not. I bet all of you are familiar with Instant NGP from NVIDIA. Effectively, that's still a grid. It's just not dense, it's hashed, but it's set up in the same way. And this follows that implementation quite a bit, apart from the fact that it's dense, it's not hashed. And we have multiple levels of a pyramid. From each level, we sample whatever is stored there, whatever was learned there. And from each level that is lower than the current level that we're trying to evaluate, we actually take the value and we concatenate them all together. So there is actually no interpolation, which allows the network to also figure out, to also use different levels for different purposes, potentially, as we have seen. But the very cool part about it is that this is effectively all the spatial information, all the UV-related information are now they're now learned by the texture. They're not learning the texture. They're not anymore something that MLP or any network they're using needs to learn. Right? That is super effective because now our MLP just needs to learn what is the correlation between whatever value it optimized in the texture and the directions that you're trying to evaluate, which makes it a bit easier. And that is kind of like the pattern all the time. If you make the job easier for the network by either enforcing geometric constraints or physical constraints, it's going to learn quicker and it's going to have less issues. And there are similar things related to that is also when you use techniques like neural radiance caching, and you're expecting it to output reflectance times maybe the emitted light, it makes sense to actually pass that reflectance at the end, so the network doesn't need to figure it out completely, as some techniques don't really do it, but we found out that that was quite useful. Yeah, again, as I mentioned, we evaluated only on the primary intersection, the red light, and effectively it is implemented by allocating a buffer that is large enough as a screen, where we're going to store all the network inputs. Of course, there is also one for the outputs. The network inputs, as I mentioned, there are the UV, the WO, the outgoing and incoming directional in tangent space. And although there are two models, we prepare a single buffer. It's just that for the reflectance models, this UV is going to be modified, right? And since different materials have different sets of weights, as I mentioned, they're overfitted, they're not generalized. So every material has its own weights and its own latent texture. We actually end up bucketing the same materials together. We make sure that effectively we can do a single dispatch per material, because we cannot run it otherwise, really, because our implementation for the network evaluation is heavily reliant on group share memory, and also doing work within the thread group. So we cannot really even afford it. And divergence, when it comes to, if you would have something that where like every other thread needs to evaluate or needs to load a complete different set of weights, that would just not make sense also. It would just be too slow, because as we will see later, memory tends to be the main bottlenecks for these models, because these models tend to be small, tends to be narrow and shallow, so memory becomes the king, I would say. But so we got these technique going. Obviously, first implementation was just in PyTorch, so all the training was done there and everything perfect. So now we need to implement it. What do we need to implement it, or to implement the inference at least? We just need to be able to do linear layers or general matrix multiplies. Or have some activations. In this case, we're using sign activations, but you know, ReLU, JALU, all those kind of names. And then we need a grid sampler. But as I mentioned before, they are effectively just texture. And since we're working with this 2D grid and it's bilinearly interpolated, and it's 4 channel per level, what can we do? Well, we just build a MIP chain of actual textures and we just sample it. So that is as fast as it gets, from that point of view at least. One small detail that is not in there is also the fact that these are F16. We have tried to scale it down on the latent texture side by doing quantization aware training and stuff like that, but that didn't really work. But the MLP, we found out that you could scale it down to int8 precision, but not really the texture. So yeah, again, it's pretty simple, right? Well, turns out that optimizing a general matrix multiply is not that trivial because there are a lot of caveats. In fact, this is the definition of a general matrix multiply, where our output y is a scalar times these two matrices A and B, and then another scalar beta times C. Effectively, A as a shape of mk or km that can be transposed. The input, the tensor B about the same, it's kn or nk. And then the final, it's just a matrix multiply, right? So if you're going to have something that is mk times kn, we're going to get something coming out that is mn, right? That's just, that is the gist here. And on top of that, actually, we also have the bias, C, which needs to be something broadcastable to the shape mn. Effectively, in practice, when it's a neural network, the shape is just the output shape, just n, as I will see in a second. So, yeah, first off, for a linear layer, we are looking actually at the simpler version of this. We usually don't have alpha, don't have the beta, so that is out. We're left with AB plus C, but even better, maybe you're more familiar with it, y equals weight times the input, or the other way around, plus the bias. But at the end of the day, bias can just be ignored. Of course, it is not exactly true from performance reasons, though. it's small enough from computation and from loads point of view that it is fine to ignore it for now. So we can just focus on the single matrix multiplication. So the main consideration, I guess, is that we know that performance of a function on a given processor is limited by at least one of these three factors. It can be memory bandwidth, it can be latency, or the math bandwidth. We can determine, in theory, a priori, right, what is going to be our peak performance or where is going to be our bottleneck by figuring out what is the arithmetic intensity, which means how many flops per second over what is the ratio between the flop per second and the bytes per second that we do, right? So how many flops we do per bytes that we access. And yeah, this it's going to play the whole video now, but effectively we know that y is m n in the shape of y is m by n columns. A is m by k, and B is k by n, which means that we're going to have m times n writes, m times k reads, k times n, and then and k times n reads as well. And since we're using F16, because of course we implemented it with F16, we have 2 bytes times the sum of these 3. So that is going to be our memory, the amount of memory, the amount of bytes that we need to load, to evaluate, to load and write when we evaluate matrix multiply. And instead, when we actually, if we want to evaluate, figure out how many operations we need to do, and that's why the video was there, effectively, we know that y, the output, is m times n values, and for each of these values, effectively, we're just doing a dot product of k element vectors, right, as you saw probably there from the animation. Which effectively end up becoming just k FMAs, right, fused multiply adds, for a total of m times n times k fused multiply adds, each of which are actually 2 operations, so it's 2 times that, which will factor out, of course. So our arithmetic intensity at the end of the day, it is that long thing there. I'm not going to repeat it again. But because we are working with such tiny networks, our worst case scenario, which is, let's say, an hidden layer with 32 features, because maybe our input is smaller, not sure, could be. Let's say we have an hidden layer where of the size of the batch times 32, and it's multiplied by another, by a weight that is 32 by 32, which actually means in practice that our n or k are 32, but I was feeling like this was too little, so let's push it further. Let's push it to 64. That is actually the size that we use for radiance caching. And by simplifying the expression, we end up with 32, effectively, right? Especially because I skipped a bit, but since m in this case, in the worst case scenario, is the entire frame, so it's maybe at 1920 by 1080. That's the wrong resolution. We have something like 2 million inputs. So effectively, that m is so big that it doesn't really matter. That plus 64 at the end doesn't really matter. So we end up with this 32. Obviously, again, it's approximated, but good enough. So I figured to compare with the card that I had at the time, so the RTX 3090, which has 35.5 teraflops of math bandwidth. And instead, it has 936 gigabytes per second of memory bandwidth, which means that our arithmetic intensity is 37.9, 38. So we can actually use this to determine the upper bound of our task. And it tells us basically that we at least need 38 operations per loaded byte to actually saturate the compute unit. But as we said right before, we just had 32. Even worse, right? If the model was 32 features wide, like we're doing for the neural materials, it is half of it, right? So this is actually pretty bad, or well, better. It tells us at least where to focus. It tells us that we need to focus on memory because it's going to be our main bottleneck. I also picked a couple more cards, just other cards that I had at disposal. so like the AMD Radeon RX 7900 XTX, has a bit more flops, quite a bit more flops, especially for F16, where they double, where it ends up having 63 arithmetic intensity. So in this case, it's even worse. And then I was like, okay, maybe we can take a mobile GPU for laptop to see and compare, because these techniques are mostly implemented for GPU, not for either desktop or laptop at the time, at least. Now we're trying to also move this to mobile, but that is taking some effort, of course. So I also took the Intel Arc A530M, and that one was a bit better, 16. 16 was actually exactly what we get with the 32 feature wide network. So on that side, looks okay. It is a bit less of a memory issues. Yeah, small notes, these teraflops are for FP32. They actually should be multiplied by 2 if you want to see them for F16. For AMD and Intel, that's the case, not for the NVIDIA card. The usual implementation, and here I have a pull request link, very nice, is we have a tau-based implementation of GEM, of the geometry multiply, that is usually the first step to move it from a naive implementation, which effectively consists in each dispatch, each group is going to take care of a single tile while we slide the tiles over the other two matrices over the k dimension, and they just accumulate there. There are plenty of articles that explain this algorithm. It's not particularly interesting from this point of view, but again, we know that the problem is going to be memory, which means that we need to do things to make sure that we do the least amount of loads and we use it as good as possible. So of course, first thing is also trying to use shared memory, and with this we can also try to achieve the minimum number of loads, but then you need to be aware of bank conflicts, which obviously will incur a lot, because we need to read over and over again the same input. But since our model weights are actually really small, they could fit in register, kind of. And then we could actually fuse all layers in a single dispatch. That is the next step that we took, or at least we could fuse the linear layer evaluation with the activation, right? So by storing input, effectively this technique by fully there was this paper from NVIDIA called neural radiance caching, where they also introduced this technique called fully fused MLP, which is implemented in their repository called breda-nn. And effectively, it works by trying to leverage in the best way possible all the hardware. Effectively, what it does is that it loads the input in shared memory, and then it loads the weights in registers. What they do there is actually loading the registers in registers specific for the other accelerators. What we actually do in our implementation with wave matrix intrinsics. And that is the best way you can get performance out of it, again. Because effectively what you can do with it is we have our input in shared memory, we have our weights in registers, we produce the next output, we now move that into the input, we move that into the shared memory, and we do that for every single layer. And then at the very end, we actually output and write that out, which again is the best use of memory that avoids all kinds of repeats. So that's great. Also, again, another benefit of using shared memory and using registers to load stuff is that you could actually, register and wave intrinsics to then share them across the lane, because that's actually how you can have that many registers. A single thread wouldn't be able to have 32 by 32, or even 32, just 32 floats. So yeah, we've used the wave intrinsics to make sure that we can do that. There was a very interesting talk yesterday that will be uploaded as well if you were not there, about harnessing wave intrinsics, and there were some interesting takes from there that maybe we could apply as well. But effectively, the deal is that we can spread the loads across all the threads, and we can make sure by that we load everything only once, and it is easy at reach for the operation that we need to do. And actually, specifically, our implementation, when we have 64 features, it's running for 128 by 64 of the output at a time. So each group processes that at once. Obviously, there are other problems when you're trying to optimize this, which specifically is occupancy. There is another talk about this, I think, today or tomorrow. But effectively, occupancy is about using all the threads per stream multiprocessor per compute unit, right? And usually, register and share memory are the main culprit, right? Which kind of incurs into one of our main problems. Now, we kind of need to design this to be able to run on every sort of GPU, but, well, we need to keep into account all the sizes of the over shared memory and registers to make sure that we can fit in the best way. This complicates things a lot, but you can get a wave agnostic implementation going. Now, another thing indeed you want to do is doing coalesced memory accesses. And one of the main things that you probably want to do is transposing your matrix P or your weights so that you can more quickly do row dot column, right? Because every single value in your output of the matrix is just a dot product between the row of the matrix A and a column of matrix B. But if we flip it, now it's row times row. Like in this case, if we transpose it, it's row times row. And effectively, by doing that, we can just make sure to load all adjacent memory, right? So that's great. Again, another thing you're going to incur if you work on this is bank conflicts. I recommend at least do not use them for group shared for accumulators, right? All our implementation tends to have the accumulator locally in a register in the thread that it's wrote out at the end, and all the rest it's and only the inputs are stored in group shared, because also that's the deal, right? You don't have infinite group shared, then you're going to occur in more occupancy issues. So yeah, there is a lot of GPUs to cater towards, which complicates everything quite a bit. The next topic I want to talk about is neural radiance caching. Effectively approximates the global light transport. And the inference consists in an input that is like X, the position. We have the outgoing and incoming direction, the normal, the roughness, the diffuse, and the specular reflectance. And it is evaluated along paths based on a certain heuristic. For example, you can use photon spread. Effectively, the NRC, the neural radiance cache, is going to have some artifacts. So what do we do is that we make sure to sample it only when the path is blurred enough so that you don't see said artifacts, which it's often also what you do with other traditional caching techniques, right? An annoying thing about it, I guess, as well as the previous techniques that we saw, is that they do not generalize. They actually are overfit for each scene, and they're trained at runtime. Effectively, actually, the training at runtime happens only for 6% of the camera paths, which are extended for a few more bounces, like 5. And we often do like something like 1 every 64 pixels that we use for the training data. An interesting thing specific about this technique that it's used in a bunch of other approaches, not specific for graphics, but stuff related to reinforcement learning, is some form of self-training. Effectively, what we do there is that our training paths, actually, we want them to terminate at sampling the NRC, unless with a light at the end, and we want to propagate it back. This effectively, again, works as some form of self-training, because by sampling the cache at the end of the path, we end up having effectively some form of infinite bounce information, if you may. Again, it's an approximation, it's not exactly that, but it is less noisy and it helps converging compared to sampling whatever you will find there. And yeah, the last thing interesting about the training of this is that the trainable parameters are actually updated with exponential moving average. They are not updated every single iteration like you would normally do with the optimizer, because we want to alleviate the harsh transition due to noise in the training data. Because of course, from one frame to the other, your training data will change a lot. And the interesting thing we have been looking into is that the original paper used a positional encoder. If you are familiar with it, the positional encoder tends to just take your position in 3D and pass it through some cosines and sine and effectively increase the frequency of the input, which becomes a bit easier for the network then to figure out what is supposed to be the reflectance or the emitted radiance in this case at that specific point. Now that is effective, but using what I mentioned before for the other technique, using a dense or an Nash grid is actually way more effective because again we move all the spatial information there, and the network needs to just learn the relationship between a certain view direction, whatever we stored in the grid, the normal that you're using, so on and so forth. Switching to a learned encoding also actually allows you potentially to generalize this, because if you were using a positional encoder or just the positions as is, the network will overfit specifically to matching a specific position to a specific output, and that is not ideal. And because of that, we actually have been trying recently to also use dynamically allocated grid based on the view, like more traditional techniques that you use for cache. It's actually what we use for our GI. Because one other problem that we have this is that the amount of empty points, right? If you're using a grid, you actually need to propagate the gradients everywhere if you want the grid to be populated. But if you have a scene, you evaluate only the surfaces, everything else you actually don't evaluate, so you're gonna end up with a lot of empty texels or voxels. But yeah, to implement NRC, we needed to create, we needed a crate because, well, we develop in Rust to train neural networks, which means not only inference, we also need training, optimizers, and a bunch of other things. But for that, we first need to talk a bit about what are tensors, at least what are in breda. They are just n-dimensional arrays with a specific shape that is useful for converting stuff. And they can be of different data types, F32, F16, int 8. What we actually use, it's only F16 for now, but we plan to extend it for all of those. And you usually have two common layouts that you use for tensors, at least for most operations. You have NCHW and OHWI, but NCHW is actually the number of samples, the channels, the height, and the width. And that is what you use for 2D image operations, like convolutional, pull, upsample, and OHWI is instead usually the layout that you use for the kernels that you use in your convolution. The other layout that we support is NHWC, so channel last, which effectively most of the times we actually just treat as N and C. We don't really care that much about the height and the width. Again, specifically, the other one is meant to be run for spatial related algorithms. And the deal is that we actually, buffers are more convenient in general for all these kind of techniques, although of course will be convenient and will probably be useful to use textures, but most of the convolutional network tends to have at least 16 or 32 channels. So using a single texture wouldn't be practical, right? So we will need to use a lot of textures, an array of textures, and just sample the correct one at a time. And again, that was felt more like an issue than something useful for us, so we didn't really go with it. Also, yeah, in the majority of these operations, we actually don't need the sampler. So using the texture feels like a bit of a forced solution. And on top of that, of course, if we need to train each tensor, then we need to store a gradient, which effectively is another tensor with exactly the same shape as the original one. As I said, we use F16, but as you know, you cannot really load one F16 at a time, nor you can store it, right? It's going to be 4-bit aligned, right? Your stores and loads are going to be 4-byte aligned, and F16 is just a single, two bytes. So what do? We actually make a promise to the user that the channels are king and they need to always be even. And what actually that means in practice is that we always make sure that the channels are even and the two channels are always stored together. And that's why effectively our shape layout is NC/2, HW, and then 2 at the end. And for the other one, about the same, but of course for NHWC, it's not a big deal. It's just the same. This makes our life complicated for some operation, especially the moving operations, but it's okay. You need to make a compromise there. I don't think you could go really around it. The next thing is that we actually wanted to support loading and exporting to Onnx, which is a file format that represents your inference with a computational graph. We figured out that there were about 190 plus primitive operations there. That does not sound feasible. Writing a shader for them, it's a lot, and yeah, as I wrote there, testing that many sounds bonkers. So we decided to take a step back and actually see if we can do a bit of a categorization of operations to determine which ones we should implement and how we can implement them fast. Two main things. You can either have it element-wise. One of the categorization that we found that is useful, it's the scope-based. If something target elements, they are going to be written a certain way. If they instead target directly axes of them or dimensions in the tensor, they're going to go through a different dispatch. But actually what we found really useful was defining primitives on archetypes. And in general, most of the operations are going to be able to implement by just using unary, binary, reduction, and movement and generators. N-ary, there are some operations that take more than one input, but all the shaders for unary and binary are the same. They take a single value, an element at the time of the from the tensor, they activate it, they apply a function, or they sum it together, so on and so forth. Reduction instead takes an entire axis or the entire tensor and it just squishes it by doing a sum over the entirety of it, or a product. Finally, the movement is actually data movement operations. For binary unary, we implemented them as you would expect, reduction more or less as well. Movement, we haven't done as much yet because although you want to move before running the next operations, it is quite cumbersome, especially with the problem I mentioned before about the 2 F16 at a time, right? And then we have generators, we've implemented them, that's great. So yeah, for training, obviously you need your usual parameters and optimizers, losses that run the forward, the training of a network effectively goes by doing a forward for the whole graph, and then do a backpropagation and passing the gradient all the way there. The gradients are calculated using partial derivatives with respect to the inputs. And effectively, when you build this, you can use some sort of direct acyclic graph. Often, it's implemented. Automatic gradients differentiation is implemented like that. Effectively, backpropagation consists in just accumulating the partial derivative using chain rule, which means we take the output of the gradient of the output and we multiply with the gradient of it, and we multiply with the gradient of the current operation to propagate a bed. One interesting thing that we did, kind of running out of time, but one interesting thing that we did was that we decided that we should split the forward between inference and training, because we know that very often, if we have a single network that needs to run both inference and training, they're going to have very different input sizes. Like we mentioned with NRC before, for example, 6% of it's training. We need to keep track of the gradients, and when fusing, we already talked about it. We actually might want to have complete different implementations, not just separate them, but complete different implementation, because you might end up that you want to write out the output of the previous layer so you don't have to recompute it again, as that would have been effectively too expensive to compute. We store everything in F16. The only thing that is F32 are accumulators, because you need that precision. But the arithmetic complexity of the optimizer tends to be very low, because you do a lot of loads and a lot of writes, but not that many operations. You end up doing some square roots and whatnot, but effectively the arithmetic complexity is quite low. So what we often do is that we find a zero or low enough gradient, we kind of skip it, because we skip all the other reads and writes, because it just makes it faster, especially for the grid, because the grid has a lot of parameters and we would have to look through all of them. And last thing is that forward and backward of a linear layer effectively looks very similar, but I don't think I have time to go through that. Yeah, so there is an interesting trick that they don't talk that much. I haven't found many people talking about, is the fact that you actually don't need to compute the forward of your loss. If you look, for example, at the mean squared error, which is a binary, a unary, and a reduction, specifically subtraction, square, and then an average, you don't really need all three outputs nor three gradients. You can do it in place because effectively the gradient is just 2 times the ground truth minus the prediction of the networks divided by n. So you don't need to compute that. That is sometimes expensive, especially to do the reduction. The rest of the operations are not that much of a problem. So actually the batch size does not matter. Well, it does, of course, because it's divided there by n. And we find that it's a very big problem, especially with floating points. And that's why you should actually also have for your gradients some scaling factor, because with F16 you're going to run out of precision on the smaller numbers very quickly. I think I'll skip this because it's a bit too late. So one of the problems that we've been trying to tackle recently is actually training neural radiance cache offline. Because we want to see if we can generalize it. We want to see if we can generalize at least a network, for example. And we're doing some other work with some of our clients. And effectively, what we figured out is that we need to have enough space P to cover the entire surface of the scene to properly sample it well, uniformly sample it, of course. And for each of these P, we need to sample all outgoing directions because like a point might be seen from the camera from many points of view. And if it's specular, we need to have enough outgoing directions to represent it. The same goes then for the incoming direction. For each of the outgoing direction, we need a certain amount of incoming direction. We found that something around 32 is a good ballpark, but the data size explodes because you can imagine how many points you can sample on a surface of a scene are going to be enough. So effectively, the challenge here is that we training even a simple scene, we found like a Cornell box, a small Cornell box with a couple extra objects in there, ends up occupying 60 gigabytes. That is really not ideal, especially for training. But since that model is small, we know that the compute is not going to be a bottleneck. The GPU is actually, we see that the GPU is underutilized. And the memory requirement also for the computing forward and backward is not a problem. So our main bottleneck is actually loading training data from this to memory. That is the main bottleneck. Solution, well, the solution is actually getting maybe more than 1 GPUs with enough gigabytes. And one thing you can do, of course, is cache training data by pinning memory on the GPU. That's ideal, so you can just don't have to reload it, you can just ongoing. And we've been using in the past few months a workstation that the sponsor of today's talk sent us for a few months for an evaluation. And we've been quite pleased up till now because having 48 gigabytes of VRAM means that most of the data is actually going to be always available for you, right? So that's great. And by doing this, we effectively minimize the data transfer and accelerate the training process by about 4 times compared to our RTX 4070 Ti and also our 3080. We see something like this. Because on top of being able to store more memory in more training data in memory, we can also do bigger batches, right? Because we just have more memory. So that's absolutely great. So yeah, this allowed us to iterate fast on our ideas faster, try more training and more sweeps, and hopefully prove value to our clients to also prove value to our clients faster by using this. And yeah, well, that is a personal thing. Also prevented us, not prevent us, maybe it's the wrong word, but allowed us to not run on our personal machines, which will just break, right? We'll just sit idle and we cannot do much more if we want to use it all completely. So yeah, I highly recommend if you need to do AI acceleration, a workstation. And that's something that I'll probably push forward also in my company because it's quite useful. So that's next. Soon Evo will release the version that will come out next year. Again, there's going to be one at the end of November. The one is coming out next year. At the end of Q4, will feature some of the ML operations, some of the ML techniques that we talked about today. And alongside with Evolve, we're also going to release parts of Breda open source. Breda is the name of our framework, if I didn't mention it before. We also plan on better supporting Onnx operator and actually implement some of the operation I talked about today and we didn't do yet. Like I completely ignore broadcasting, for example, because we don't need it. We don't see the point of it, right? And maybe work graphs for neural network library. That's something that we are very interested to try it. There was also the workshop from yesterday. Fortunately, I was not able to attend, but we already have some versions working for work graphs for a render, and we'll try soon also see if the neural network library benefits from it. So, all in all, I recommend start simple and try to figure out step by step, especially try to figure out the problem, exactly your problem space, because the size of your network is going to matter. The type of data, the training data you need to use, it's going to matter a lot. So don't start by wanting to implement them all the operations. That doesn't make sense, because not all neural networks are made equal at all. If you want to support a big matrix multiply, it's going to be a completely different implementation than what we talked about today. But implementing a good set of operation, it is very possible if you do this kind of categorization and implementation of the primitive operations. Unfortunately, precision is a pain, especially if you need to do training. So be careful with that. Scaling factor for the weights is a great help, but it tends to be a problem. And the amount of data to fit something to approximate global illumination, that is just too much. I was not expecting that was going to be that big of a problem. So thank you, everyone. Special thanks to the organizers that invite. I'm also part of the organizers. Initially, there was no idea to do this talk, but we want to present something from Traverse, and HP wanted to sponsor this, so here I am. So thanks for HP for sponsoring this talk and also offering us this nice machine that we've been using the last few months. Yeah, and thank you, everyone. Do you have questions? Thank you.